happens. And there's an additional Proth structure. And we can assign this high energy peak to argon ions that are directly scattered at silver target particles. And this peak relates to argon ions which are scattered at implanted argon ions. So if you bombard the surface with argon, also argon ions get implanted and they act as scattering partners. So you have two peaks, one peak for argon at silver, one peak for argon at argon. And this is also called anisotropy effect because it's related to directly scattered particles. So it's the wrong word. So you have the same, similar to the sputtering. You have also a simple equation which is given here, but we have to understand that there are two regimes. Either the projectile is smaller than the target particle, or either the projectile is larger than the target particle. And you see this term here under the square root. This must be positive. So you see that in this case, in the second case, so the scattering and the maximum scattering angle is limited to this value. I plotted it here. So if you have the first case, you have all scattering angles allowed. But if you have the blue, you have only those smaller range. And this range is limited by the maximum scattering angle following this law. And what that means, we see on the next picture. So we plot the same for here's argon on silver, here's xenon on silver, and we have the same curves with the same scattering angle, same energy, same ion incidence angle, and you see some similarities. The similarities are this additional structure. It's here, but this high energy peak is totally missing. And this is related to the fact that the primary particle, xenon, is larger than silver, and argon is, the mass is larger, and argon, the mass is smaller than the target particle. So here we have what we already explained. We have a larger scattering angle range than in this case. So this peak is missing. It should appear at an angle of less than 55 degrees. So at 50 degrees, we would expect the peak at about 250 electron volts. At gamma 40 degrees, it would be somewhere around 500. It's not here. Perhaps it's subsumed by this broad structure. I'm not sure, but you see the difference. Keep this in mind. We will need that later on. So again, we have here our curves from before. In one diagram, we increase the ion incidence angle, plot the curves with the same scattering angle in the same color, and you see that the curves are similar. Here are some curves more, because if you have a higher ion incidence angle, you get more scattering angles. And if you increase the energy, you see that these high energy structures shift to higher energies. And also the Proth structure extends to higher energies, but the energy maximum is very similar. So this again is a good correlation with the equation where we say the energy of the scattered primary particle depends on the ion energy and on the scattering angle, or if we compare different ion incidence angles. So in summary, so we have it's a small plot. It's basically there are some cases where this is not really true, but in order to make it sure. So if you increase the ion energy, you get a higher flux of particles. The energy and of the sputtered and scattered particles, the average energy increases. If you increase the ion incidence angle, you have a higher particle flux. But if you go to the energy, you cannot really talk about the ion incidence angle. You have to consider the scattering angle. So if the scattering angle decreases, the energy goes up. And if you have an increase in particle mass, then you have also the relation of the primary particle mass to the target particle mass. So the flux is increasing, the energy, there's a maximum if the energy is the same, and the energy of the scattered particles goes down. So this is the summary of the particle properties, and this somehow, if you do ion beam sputter deposition should also be reflected in the particle in the thin film properties. So the first is the composition. So we have here plotted always over the scattering angle, because we have seen from the particle properties that the scattering angle is most important. And now we plot here the amount of argon particles and xenon particles in silicon dioxide films, in titanium dioxide films, and in germanium films. And what we see for different combinations of ion energy and ion incidence angle, if we plot the curves over the scattering angle, they coincide perfectly for all of these systems. So the driving parameter is the scattering angle. The only difference is that you have here a case where a large amount of argon, and here you have cases where the amount of xenon or argon is much lower. And I have here a green cross. The green cross says if the primary particle is heavier than the target particle, then we have a low implantation. Of course, if it's heavier, it gets less scattered, so we have less in the films. Some kind of optical properties, again plotted over the scattering angle here. That's titanium oxide films, silicon oxide films. Over the scattering angle, we use oxygen ions, argon ions, xenon ions. You see some systematic shape, which systematic variation with the scattering angle, and also a much higher dependency on the ion particle. So it's particle mass basically. So the higher the particle mass, the higher the index of refraction. Here it's some similar effect, but look at the numbers. So the numbers are very small for silicon dioxide, but for titanium dioxide it's huge. And the driving parameter is the mass density or the particle density. So depending on the ion beam, the ion species, energy, angles, and so on, you get a correlation between the index of refraction and the mass density. So red is xenon, blue is with argon, oxygen is green is with oxygen. So you have a variation of the index of refraction by about 0.5 with one experiment, just by changing the geometry and the ion source and the ion energy. And this fits quite well to a general picture. So you have different sputtering, different thin film deposition techniques. Here I have filtered arc. Then there is the sputtering, mainly I think it's called, in the older days they are say only sputtering, but it's a magnetron sputtering. And you have here with the small mass density and index of refraction of these evaporation techniques. So now let's come back to silver. I told you there's a huge difference between sputtering with argon and xenon. So for argon you have high energy peaks which are missing for xenon. And here you have a totally different picture if you use argon or xenon. So for xenon, the electrical resistivity is much lower. So the shape is almost the same, independent of the parameters you are using. It's basically also driven by the scattering angle. This is much different. And this is also reflected in the average grain size. So we did some structural characterization and determined the average grain size. But even though this systematic behavior is different for xenon and argon, and this is probably related to the fact that you have not only grain boundary scattering, but for perhaps some other additional scattering effects, processes, which make this resistivity much higher for sputtering with xenon as argon than for sputtering with xenon. So I hope I could show you that it's a challenging but interesting process to study. I forgot to say the challenging part is that when you're measuring secondary particles, you have an incident ion beam, which is collimated or focused, and the scattered and sputtered particle, you have the angular distribution. So they are spread over a large range. So basically, the number, when you look at one point with a small orifice, the number of particles is small. And we are looking here at ions. We could not measure atoms, but if you know something about sputtering, then you know ions are normally just a few percent or much lower. So normally the sputtered particles are atoms. But still we were successful. That was really nice. We have some nice systematic correlations. It's not done, wasn't done before in this extent, so especially when you correlate particle properties and film properties. And still lots of open questions. So the point is now we would like to combine these expertises in ion beam etching and ion beam sputtering, so this particle knowledge, because if you have an etching process, you remove material, secondary particles, and these secondary particles may have an effect on your workpiece, which you do not want, redeposition, resputtering, and so on. So it's very, very important to know the properties of these secondary particles in order to avoid these unwanted effects, or at least minimize them. So if you want to have something more about the ion beam deposition, there are some publications I did. This is what where you find most of what I said. And this is what I wrote some years ago on the history of ion beam source developments in Leipzig, so 50 years. And if you want, I have some copies with me, so just come and get a copy. So thank you very much for your attention, and there are lots of people. Here is the group which are directly involved in these ion beam sputtering experiments, either particle or thin films. And here a lot of people have this analytics, and of course there was some funding, so thank you very much.
And we have time for some questions. Yes, in the back.
It would be also very interesting to learn about the neutrals, energy distribution of neutrals. Can you comment on how far we can get these devices to measure neutrals?
Well, yeah, it is possible to measure.
And the point is, you have an ion source inside your ESMS. And the higher the energy of the particles, the less is the time they are in this region. So we were testing it with another device, and so we are able to measure secondary atoms, ionized, post-ionized secondary atoms up to about 100 electron volts. And then we figured out that the intensity was too low to measure something. But what we did is we did some simulations, these TRIM-SP simulations, and they showed very similar shapes, so we are quite secure that it's a similar shape for the atoms as well. Now the point is, of course, Barry Krokam will talk about this a little bit later, so that the transmission rate of this ESMS depends on the mass, and the acceptance angle depends on the energy. And you never know the exact function which is behind it. So what we see here is not what really is there. It's always some kind of distorted with this mass sensitive transmission and this energy dependent acceptance angle. But if this wasn't done before, then it's better than nothing. Or some old colleague said once, it's the worst I know, that's the best you can get.
So then I think if you have such high energy atoms, we can work with pole bias or not?
Yeah, it's possible. It's possible again to bias the system, to look at energies above 1000 eV, around 1000 eV. Again, with the same technique that you mentioned, with the what we call fast neutrals, so highly energized neutrals. It's a case of using the electrostatic lenses on the front of the system to repel the ions, and then the ionization source is tunable to selectively ionize the species that you like, the neutral species that you like, and then then they will have their kinetic energy as they go through the filter, and then you've got a chance to measure them with the quadrupole, which I think is what Carsten pretty much said.
So if you have always an issue with such things, you need to ask the experts and from us.
We have, well, maybe Sam and the applications group for plasma, myself as well. We have a lot of techniques that if you ask us, then we can go through them. They're not necessarily in the manual, but they will be from helping other customers, or we can put you in contact with someone else who's done the same thing, which has been really good today, I think. Any more questions?
I had exactly the same.
Okay. Okay.
But maybe, do you have feeling about the quantity of reflected neutrals, organ neutrals? It's of course depending on the sputtered material, but are we talking about 1-digit percentage, 2-digit percentage? Can you guesstimate anything? I mean, you can simulate it using PRIM. There is a result, yes, but
as I said, it's really not that simple. As I said, you have a mass-dependent transmission and an energy-dependent acceptance angle. So, and you don't know how is this. For instance, you not know how is this energy or these particles distributed over this acceptance angle. No? So that's why this. I always say the systematics is nice, and this is true. Huh? Quantitatively, it's probably not that easy. You also cannot use these numbers from the composition, because if you have an energetic particles hitting a surface, then normally primary particles they are just outgassing. So this noble gases. But we have here a certain number up to 10%. That means they must have a certain energy in order to get deeper into the growing fill, in order to be able to stay there, not to get out again. So that's why this number is probably related to some high energy argon ions, but we saw that the low energy peak was several orders of magnitude higher. But still we see that this small number, even though it's several orders of magnitude smaller than the low energy part, plays an important role. By just comparing the data for silver with argon and xenon, you see there is a difference, and the only difference in the particle properties are these high energy scattered primary particles. So,
okay, any more questions? Okay, great. Let's thank you. And our final speaker this afternoon is Dr. Eric Broekman.
Okay, so thank you very much. My name is Eric Broekman. I'm as well from the Leibniz Institute of Surface Engineering. I'm doing my PhD thesis there, and I'm part of the group ion beam assisted patterning and smoothing. So we are mainly interested in the ion beam etching processes and further optimizing them. So Carsten already talked a little bit about some applications. For these produced optics we can do with ion beam etching technology. And as you can see on the left side, there's one optical grating that was produced at IOM. It's a binary grating. You can see a profile measurement at the bottom. And the main benefit of ion beam etching technology is that you get these very nice, precise profile shapes and a very high accuracy concerning the profile depth and the width of your profiles. So in that case, we have a profile height of 600 nanometers and a periodicity of 700 nanometers. And of course, you have a lot of different applications in the optical sector for these optical gratings. And one of the best applications to show in presentation is always some space applications. So today I brought a picture from the European Space Agency Sentinel-5 operation. There's a satellite orbiting Earth and it's recording the radiation emitted by the Earth's atmosphere, and that is used to measure the composition of Earth's atmosphere, especially regarding greenhouse gases. So you can have a scanning of greenhouse gas composition of the atmosphere all over the Earth, and what is there used is an optical grating with a blazed structure. It's not a binary structure, but a blazed structure, so a triangular shape that was also produced with reactive ion beam etching. But there are also some challenges we have to accomplish when we want to produce such gratings. So it's always easy to do that in the lab on a small scale, so you have your 1 by 1 centimeter samples. But the biggest challenge is to have these precise profile shapes and your very low surface roughness. We speak about sub-nanometer surface roughness, RMS. You have to bring that to the large area. And here's the problem that your ion beam source, we're using an ion beam source with 120 millimeters diameter, that is much smaller than your substrate you want to process. Therefore, you need an access system, so you need a relative motion between your ion beam source and the substrate. But the consequence then is you have very long process times. So we're speaking here from 10 hours to up to 100 hours of process time, and you can easily imagine that the ion beam source performance you get, so the removal function of your ion beam source, is varying over that time, and in order to achieve a very precise profile shape, you exactly need to know what is your removal function of your ion beam source. So how is your ion beam etching process varying over time and evolving, and you want to predict that in order to have a better results. So what we are talking about is inert and reactive ion beam processing. So the more easier case is inert ion beam processing, where you use argon, for example, in your ion beam source. You accelerate that towards the sample, and there you have your erosion made by ions and neutrals. But when it comes to reactive ion beam processing, you're not using argon, but mixtures of different reactive gases, such as CF4, CHF3, oxygen, and so on. And beside ions and neutrals that are accelerated towards the sample, we have a lot of fragmentation processes inside of your plasma chemistry happening. And beside ions and neutrals, you also have radicals, which can have a very high etching potential or even a deposition potential onto your sample. And you really want to know, okay, what kind of species has what impact on my substrate. So that is why we are interested in the characterization of our ion beam. And as an example, I've recorded a mass spectrum from our ion beam. So we're using an RF excited ion beam source, and that one is fed with a mixture of trifluoromethane and oxygen. And since you only put 2 different gases inside of your ion beam source, you do not only get CHF3 plus and oxygen, O2 plus ions, but you get a lot of different species in your ion mass distribution at your main ion beam energy. So when you count that, when you go to logarithmic scale and count these species, you have over 30, over 40 different ion species. So you can easily imagine that this process, which is depicted on the right side, the plasma chemistry happening for the decay of trifluoromethane in the plasma, is very complex, and all these different ionic or radical compounds of your plasma have a very different etching behavior. And our idea is now to use energy selective mass spectrometry to get an overview or first hint what is happening inside our process. So to the experimental setup, as I already said, we are using a RF excited ion beam source, which is an inductively coupled ion beam source. So we have our plasma discharge vessel, which is made out of silicon oxide. We insert our process gas, and by the surrounded RF cable, we are inserting energy into our gas to ionize it. Then we have a plasma, and this plasma is extracted with a focusing 3-grid extraction system, which is made out of graphite, by applying different voltages to it. We are using a commercially available ion beam source from SPA Systems. It's a company here in Saxony in Chemnitz, and we are mainly using different gases, argon, so different noble gases, and our standard mixture for etching is trifluoromethane and oxygen. But this mainly depends on what you want to etch and what your result, how you want your result to look like. So by applying different potentials or different voltages to your grid system, you have this potential curve along the ion trajectory of your ion beam source, and you can see that your ions are created inside of your plasma discharge. So they are at a potential UB, which is your grid 1 potential, plus a typical plasma potential, which is in that case somehow 20 volts. And now your ions are accelerated towards the accelerator grid, then a little bit decelerated, and are then leaving the ion beam source and propagating towards your sample or towards your energy selective mass spectrometer. Here's a picture of our vacuum chamber of our ion beam etching system. So normally when we do an etching experiments, we have a cooled substrate holder here. We also have a Faraday cup array for measuring the current density distribution, and of course the energy selective mass spectrometer mounted to the wall. And we are able to move our ion beam source in 3 different directions and to rotate it. So we can provide different distances between our ion beam source, our diagnostics, and also different angle of incidences for our ion beam. Yeah, it's quite nice that I can be a little bit faster over this slide in that meeting here. So we're using energy selective mass spectrometer from Hiden. We have several different at our institute, and in this talk I will talk about the EQP6, so a 6mm system and a 9mm system I was comparing, and it allows us for mass ranges between 0.4 to 150 AMU for the EQP6 and 1000 AMU for the EQP9. And we also have the high energy range additional package, so we are capable of detecting ions up to 1100 electron volts. And what I want to focus most about is when it comes to a determination of the composition of our ion beam, the most challenge is the, as Carsten already mentioned, the mass-dependent transmission function. So on one hand side, we have the angular, different angular acceptance angles for ion energies, but since we are operating in an energy range over 100 electron volts, this is almost constant. So the highest problem is the energy, the mass-dependent transmission function. And there's some mathematics here, which is a solution for the quadrupole section of the mass spectrometer. But the most important fact is that the mass resolution is dependent on the mass itself. So in that case, you have different transmittances for your ions with different masses. And that is a challenge when you want to quantify the composition of your ion beam. So Hiden also has some data available in the internet, as you can see here. There's the mass and your sensitivity of your EQP. And you can see that you have kind of an exponential decay here from your sensitivity to your mass. But we wanted to measure that for our EQP system to have a look what our mass-dependent transmission function looks like, because in several publications you find that this transmittance is very dependent on the tuning of your EQP. And therefore we are needing the RGA mode of our ESMS, and we insert different process gases, in that case all the noble gases we found at our institute, to insert into our chamber and to ionize it. And the experimental workflow is mainly similar to that presented by other authors. So we are inserting the noble gases, we ionize them and detect them at our detector. And since we are measuring a signal at our detector, we need to know, okay, how many ions were created in our RGA section of the ESMS. And therefore we need the abundancy of the isotope we are looking at of the noble gas, the partial pressure inside the RGA section, the ionization cross-section, and a device-specific factor. So this device-specific factor is typically not known, But since we are only interested now in a relative amount of ions in our ion beam source, that is not so much a problem. And the partial pressure is not exactly known, so we can measure pressure in our ESMS, but the differences in pressure is so small that we decided to use another technique. So we measured the pressure inside of our vacuum chamber, and with several assumptions, so we have a molecular flow regime, we can estimate the pressure inside of our ESMS for the different noble gases. And when you apply that to the formula, you get some kind of transmission function for your ESMS, dependent on the mass of the different ions you are creating. And these are the data I want to show you now. So we have done that for our EQP6 and for our EQP9 system. And what you see is the curve already shown by other authors, that you have a maximum at above approximately 20 to 40 AMU, and you have a decrease of your transmission for higher energies, for higher masses, and also for lower masses. And when you compare now these data of your 6mm system, of your 9mm system with the function provided by Hiden and the simple 1/m approach, you can see that these functions fit quite well. In the case of the 6mm system, between 20 and some kind of 60 to 80 AMU, but in the case of the 9mm system, you can see a relatively high deviation, especially for lower and higher masses. So what is that saying to us? So in some cases, these data are quite good when it comes to quantification of your ion beam composition. But if you want to know it really well, what the composition of your ion beam is, you need to do these pre-tests to determine your mass-dependent transmission function to have a very valuable result. So I've done now a quantification of our composition. So we are using again our trifluoromethane and oxygen process gas. We have recorded all ion energy distributions, and then we integrated them to see, okay, what is the actual composition of our ion beam. So on the blue bars shows the composition without any mass correction we have made, and in that picture you can see the comparison of the different mass-dependent transmission functions, the two we have determined, and the one by Hiden and by the 1/m approach. And as you can easily see from that picture, so here the curve for the 6mm system, Hiden data, and 1/m approach is approximately equal. And you also see that in these data, so the orange, the light blue, and the green bars are almost in the same order of magnitude, but the red curve, so the EQP9 system, which was used here for recording these data, show a relatively high deviation from the other data. Okay, so what ion energy distributions have we used? These are the ion energy distributions we've recorded. So we've recorded, I've written it here, I think there are 18 different ion energy distribution functions of our ion beam. And here are depicted the ion energy distributions for our CF species. And what you can see is that you have different contributions in your ion energy distributions all over the whole energy range. So we applied a beam voltage of 700 volts. So we expect our main contribution at our beam potential plus plasma potential, which is correct. So these ions in that part of the spectrum are ions produced inside of your plasma, or of our plasma discharge vessel, extracted and then detected by our ESMS. But you also see amounts in the lower energy range, and these are fragmentation processes along the propagation of our ion beam. So what is happening here? We have a heavy ion which is colliding or somehow interacting with residual gas particles or with other parts of our ion beam. Is then dissociating, but the energy is split regarding to their masses. And you can do some calculations, and when you calculate all your different fragmentation patterns, so your CF CF3 is dissociating into CF2 and a fluorine atom or radical, and you can assign all these different peaks to a single fragmentation process. And this ion here, CF2 ion with 507 electron volts, can dissociate further into even smaller fragments. So for example, CF plus at 314 electron volts, and you also see a peak here in the spectrum. So what you see is that when you apply a voltage to your ion beam source, you have to be aware that you do not have a monoenergetic ion beam, but your ion beam is consisting of several different parts in your ion energy distributions. You also have very slow fragments, very slow ions, which of course have a very different etching behavior in your etching process later on. And in the case of very light species such as C plus or CF plus, they can even lead to a coating of your etched sample. So you have a picture of the dissociation process. So you have a very high or a heavy ion which is dissociating into smaller fragments, and by assuming energy and momentum conservation, of course, you can calculate that the energy is split regarding the masses. So to sum up a little bit, so we have determined the mass-dependent transmission function for two EQP systems, and what we see is that they are quite different concerning their tuning, and when you want to have a correct quantification of your ion beam composition, you really have to measure that on your own. And when it comes to the composition itself, we see that the reactive ion beam consists of many species. They have a very complex ion energy distribution, and they have different influences on the etching behavior, and that's also the next step in our research. So we want to correlate the ion energies and the composition of the ion beam with our ion beam etching process itself. And the process is outside of our ion beam source, so all these fragmentation processes play a very important role in our etching process. Yes, and with that I want to thank you for your attention, and also a lot of colleagues which participated in that work. And with that I want to be open to your questions. Thank you.
Great, we've got time for some questions.
Was a great talk about our products, huh?
I think so, yeah.
So
really enjoyable.
Better data than we have in our process. Huh?
Well, yeah, it shows that how conservative our data is in our literature as well, which is really interesting. So we would be interested to have some of the data about the mass-dependent transmission.
There's
if you could provide us with that. Yeah, that's great. Yeah.
That's really great results. So we was already also a little bit time, and yeah, it's great what you have done there.
Thank you.
Thank you very much. Very impressive.
Yeah, that's great.
Yeah.
So if you have some etching species, do you expect any degradation of the QP?
Yes, we do. So what we in some two talks earlier, it was mentioned that the orifice is coated. So in our case, we are actually etching our ESMS, so our orifice. So we have to consider about or take care about our orifice. So we start with a 50 micrometer orifice because it's the smallest. We need to lower our intensity, and over time we see an erosion, so widening of our orifice. I think in the worst case it was 700 micrometers afterwards. So we really need to replace it regularly. Yeah.
Okay. The smallest orifice that we can supply is, I think, it's 20 microns. So maybe we could look at supplying some small ones too. But certainly 700 microns is going to create some high pressure in the EQP.
But actually, it was very good for these experiments concerning mass transmission because you have a very high amount of gas entering your ESMS. So we had a very good signal there. Yeah.
Yeah.
So we were able to reuse it.
It's very good. Yeah.
Did you also notice something about fluorine concerning degradation here?
Yes, actually, we thought about it because I don't know if the channel from detector is coated with silicon dioxide or so. So we asked Hiden also, he said it's not a problem, and we see that there is a degradation of the detector, but I think that's quite abnormal because you use it and you're measuring. What we see is that the detector, we have to replace it every some years, so every 3 years or 2 years, because you can see, of course, some degradation. But actually, there are very small amounts of fluorine entering your ESMS, passing the mass section and the energy section. So I think it's not that big a problem, but actually I cannot compare it to other cases because we're always using fluorine gases.
And in your experiment, did you exchange the 6mm quadruple with 9mm on the same EQP, or you had a completely different?
Yeah, we have. I used 2 different EQPs at our institute. Actually, because the 6mm system was broken, I think we got it back these days now. Yeah, but that was quite a good possibility to measure that mass dependent for different systems, and yeah, so we have both at our institute.
Yeah, we spoke also about if you are using bigger rods, that you have a much better resolution also, and
yes.
that was also a big topic between us to split CO and nitrogen from each other, but we were not able to find a solution because it's not really easy. But it would be very interesting to see that sometime in the future that we are able to do it also with a 9mm system, because it's possible. We have done measurements, the issues only that the peaks must be on same heights, and if the one peak is much smaller than the other, then we have a big issue to resolve.
Well, it is possible. Like any of these, when we're right at the edge of performance, then we don't want to release it as a product without being fully sure that, okay, if you have 1% of CO in nitrogen, that it won't get lost in a tail in that situation. So yeah, it's something that we can do, but it's something we're working on commercially to look at that specific example. The zone H is much better for that kind of measurement than a higher frequency RF in zone 1. So yeah, it's something that we're close to releasing, but we haven't released it.
We talked also about no, we can't use it. With AKP, TIMS we can't use it because we have no iron. We don't need. That's the topic of answers. Okay. TIMS, I mean TIMS.
Yeah, for neutral species, then yeah, we can use thresholds as well, which we do. We can if we have the mass resolution, we can sit on the two peaks and look at them, look at the ionization cross sections in neutral species as well. But you can also look at the ion energy distribution if they're ions as well. So you can, I think Sam's presentation showed that if you have adjacent peaks, then you can, if you have the resolution, you can sit on each one of these peaks and look at locally either the ionization distribution or the electron energy distribution. But again, yeah, this is things that we're developing at the moment, and if you're interested in any of that, then we have a lot more information as well that goes for everybody. Any more questions from the floor? Okay, well, let's thank our speaker.
Yeah.